Okay, this is lesson 3.7, rates of change in the natural and social sciences. So we're going to do several word problems. I'm just going to review this very quickly. So remember, we started out taking a look at the slope of the secant line, delta y over delta x. That's y2, or f of x sub 1 minus f of x sub o minus x sub 1 over x sub 1 minus x sub o. So that's the slope of the secant line. You did that in 171. That's known as the average rate of change. Then we learned what would happen if we renamed this distance between these two x values h, and we saw what would happen is the distance between the two, otherwise known as delta x, if we made that distance go towards 0, then instead of having 2 points, you would have 1 point, and this would move to a tangent line. So the derivative is equal to the limit of the difference quotient as h, or the distance between the two x values, goes to 0. And that gives you the slope of the tangent line to the curve at any point. But we want to shift gears and talk about word problems, so we want to remember that the slope of the tangent line is the change in the y per a change in the x units. And when it's the slope at one point, the slope of a tangent line, it's known as the instantaneous rate of change. So we're moving from the average rate of change to the instantaneous rate of change. Okay, so we're going to look at functions of different various sciences and learn to interpret the derivatives as a rate of change. So you want to make sure you really pay attention to your units. Okay, so again, let's skip this. The slope of the secant line is the average rate of change. And the slope of the tangent line is the instantaneous rate of change. Instantaneous. And that's the last time I'll write that. So we're going to call this the arc, and this the IRC. And as far as units go, just always remember we're talking about delta y over delta x, whether we're talking about the arc or the IRC. So the units on these values that we're going to get are always going to be y units per x unit. Okay, so our first example, suppose the graph below represents a person's weight as a function of time. Well, the first thing I'm going to always do is write my math English dictionary. So we're talking about a person's weight as a function of time. So my input is t, and you can see that from the graph it's in years, so I always write my unit down. And the output is a person's weight, known as WT. Now I'm going to tell you to do two things, not just the unit, but I'm going to tell you to write down the name of the function. This is a person's weight function. This is a weight function. And the weight is given in pounds. Okay, so we want years, weight, pounds. Okay, first thing, can we read the graph? What was the birth weight of that person? Well, birth weight means what do you weigh at year 0 when you're born. This is 30, this is 20, this is 10, so it looks like about 7 pounds. Okay, next question, what was the average weight gain per year from birth to age 15? So what we want to do is we want to take a look at the ordered pair at birth, which would be 0, 7, and the ordered pair at age 15, which here's 15, looks like it's right there, so 90, 100, 110. All right, so now this is an interval. The interval is 0 to 15. So this is 2 points, so we're finding the arc. It's delta y over delta x. So it would be 110 minus 7 over 15 minus 0. Okay, and that is going to give me this 103 over 15, but I'm going to hit the squiggle and round it to 2 decimal places, so 6.87. The reason I want to do that, I'll explain, is let's do the units first. 6.87. So we can see what we did. We did delta y over delta x. So our units are going to be y units, pounds, not just pounds, but pounds per year. Okay. So the reason I gave you a decimal there is because I always want my average rate of change or my IRC to be a unit rate, a unit average rate of change, so that I could compare it to different time intervals of time. And so if I compare the weight from 0 to 10, see that rate is going to be a lot different. And if I make it over 1, then I can compare. So that's why in a word problem, I always want to divide it out. I don't want to leave it as 103 over 15. Okay, let's do this again. What was the average weight gain per year on the interval from 15 to 18? So that would be 15, 110, and I'm going to say like 1882. And so my arc would be 82 minus 110 over 18 minus 15, which would be, and I hit the squiggle, negative 9.33 pounds per year. Okay, so now we can compare this. Between ages 0 to 15, his weight was increasing at a rate of 6.87 pounds per year. But between 15 and 18, his weight was decreasing by 9.33 pounds per year. And this is an average rate of change. So if we wrote this out, it would be between 15 and 18 years. Always add your units. And this is why I always say write the name of the function, because sometimes people say the arc. When you're interpreting the arc, you don't interpret using the word arc. What's changing is this function. So between 15 and 18 years, the weight is decreasing or decreased at a rate of 9.33 pounds. Sometimes people stop there, but it's not changing by 9.33 pounds. It's changing by 9.33 pounds per year on average. So that's how you interpret the arc. Okay, then it asks, what is the instantaneous range in weight at t equals 15? So at t equals 15, we seem to be right here at the top of where his weight is increasing, but then it's decreasing. So at that instant, what is the slope of the tangent line there? So we move him from a secant to a tangent. It looks like the instantaneous rate of change in weight is 0. You still have the same units, pounds per year. And then E, what is the sign of the instantaneous rate of change in weight at 25 years? Well, remember, instantaneous rate of change is the slope of the tangent line. So it looks like that slope is decreasing, or as you go left to right. So the sign of the instantaneous rate of change would be negative. Because we're looking, the instantaneous rate of change is the derivative. It's the slope of the tangent line. It has y units. It has units, y units per x unit. Okay, so that was actually a review from test 1. All right, example 2 says if a ball is thrown vertically upward with a velocity of 80 feet per second, then its height after t seconds is s equals 80t minus 16t squared. So I'm going to write down what my input is. My input is t, and it is in seconds. and my output is s of t. Ball is thrown vertically with a velocity of 80 feet per second. Its height. All right, so this is the height function. And they aren't giving you units, but if you look here, you can see that you're in feet. All right. So the function is given, but notice the velocity is 80 feet per second, and that's right there. Okay, now we want to figure out what is the maximum height reached by the ball. Well, you may remember in 171, you could use negative b over 2a. Well, now we're going to use calculus because I know what this looks like. I'll just sketch it. We know it s equals negative 16t squared plus 80t. So we know it's quadratic, so it looks like a u, and that negative turns it upside down. So we're looking like that. And the maximum height, you can see where it is right there at the vertex. And one of the cool things that you can do when you want to find the maximum or the minimum of a function, if you can spot where the slope of the tangent line is 0, which happens at maximums and minimums, then you know that you can find the slope of the tangent line. How? By taking the derivative. So instead of using negative b over 2a, which only works for quadratics, we can take the derivative, set it equal to 0, and find the maximum or minimum for any type of function. Okay, so let's do that. So s prime of t, the derivative would be negative 32t plus 80. And then we're going to set that equal to 0 because this is the slope formula. And we know the slope at that spot is 0. So negative 32t equals negative 80. And a negative 80 divided by negative 32 is 2.5. And t is in seconds. So now we know at 2.5 seconds, the ball has reached its maximum height. Okay. Next question, what is the velocity of the ball when it is 96 feet above the ground and on its way up and on its way down? Okay, so this is a really important concept. I have room here, so I'm going to go ahead and talk to you about it. So this s of t in this example is the height in feet. Well, it's the vertical height, so we can say it's distance, or position. We can call this distance or height or position. And the particular units are feet. It could be feet, it could be meters, it could be miles, it could be any distance. And if we take that first derivative like we just did, s prime of t, and if we think about the units, then s prime of t is y units per x unit, so feet per second, and you can see what it is. It's velocity. So the first derivative of a distance or position function is a velocity function, y units per x unit. All right, now it's not asking about this, but we'll go ahead and finish this little chart out since we have room. Now, if we take the derivative of the velocity, right, that's the second derivative of position. Okay, so we still have our input. It's time in seconds. All right, and then our output for s of t was feet, and the derivative would be feet per second. And then if we take the derivative of this derivative, what we're going to have is this is my y unit, feet per second, per my input second. So feet per second is otherwise known as feet per second squared, which is otherwise known as acceleration. Okay, so it's really good to remember this backwards and forwards. All right, now back to this question. All right, so it says, what is the velocity of the ball when it is 96 feet above the ground and on its way up? Okay, so we want to think about how to find this. So what we have here, let's call this V of t, because it's S prime of t. So it's V of t equals negative 32t plus 80. And what this is saying is that if I give you time in seconds, then you'll be able to tell me the velocity. This is a good function too. If this one says if I give you time, then I'll be able to give you the vertical height. Okay, so how would we answer this question? What is the velocity of the ball when it's 96 feet above the ground on its way up? Well, do we put 96 in here? No, because that's t time in seconds. So this problem is asking us to find the time when the ball is 96 feet above. That's a position. So what we have to do first, and we'll do it right here, is set this position function, negative 16t squared plus 80t is equal to 96, which means we're going to have to use a calculator. I know some of you know how to do this, but we want exact answers when we are not doing a word problem, so you have to be careful with this. So we can use a calculator. It has a polysolver on there, so let's use it. So you can find it right here above the cosine. It says polysolve, and when you hit second and then the cosine, it will say number one, ax squared plus bx plus c equals 0. So we want to choose that, and then we're going to put negative 16 for a, and 80 for b, and negative 96 for c, and then it's going to solve it. And this tells me we could have factored it, but I'm trying to pick up some speed here. You got two answers. X is 2 seconds, or t is 2 seconds, or t is 3 seconds. Okay, so now we know when the ball is 96 feet up, there are two answers, 2 seconds and 3 seconds, or 3 seconds. So which one do we want? Well, it says we want the one that's on its way up. So this is where the picture can help. And there's another way to do it, but I'm just going to use it. So we want 2 because you can see that the ball is going up at 2 seconds. All right, so the velocity of the ball when it's 96 feet above the ground on its way up, that means we're going to do next v of 2 and plug it in. And that velocity function's right here, negative 32 times 2 plus 80. And what would the units on that be? 32 times 2 plus 80, 16. Velocity is feet per second, y unit per x unit. That's the velocity on its way up. And then on its way down, that's happening at 3 seconds. And we're getting negative 16 feet per second. Okay, so what is going on with that? Well, it turns out velocity can be positive or negative, because velocity is going to tell you direction. Not only will it tell you speed, which is the absolute value of velocity, it'll tell you the direction. So at v of 2, when you're on the way up, you can see it's positive 16 feet per second, and you can see it's going up. Slope is positive. And then at 3 seconds, the speed is the same, but by the negative, you see it's going down at a velocity of 16 feet per second. So the sign of velocity will tell you the direction that it's going. Positive would be up, negative would be down. Okay, I want you to flip over now to page 28, because we want to just continue this thought here. It's a pretty important thought. Okay, so I've already mentioned this, so we'll mention it again. The second derivative, in general, the second derivative can be interpreted as the rate of change of a rate of change. And the most familiar second derivative is acceleration, which is the derivative of velocity, or the instantaneous rate of change of velocity with respect to time. So here's what I wrote on the other page. S of t is going to represent position or distance or height. The first derivative of S of t is velocity, and the second derivative of S of t is the first derivative of velocity, which is acceleration. All right, so this is a very popular, I mentioned this, I think the first day of this unit, rectilinear motion or straight line motion. This is a really, really important application. All right, and it is this. Suppose that we have a function, S is in meters, T is in seconds, and here it is, and you're told it represents straight line motion. So I'll tell you that an object will be moving, and I'm going to write down my Math English Dictionary. So T is time in seconds, and S of T is the name of the function. It's giving a position of the object, and it is in meters. All right. Okay, so the way this straight line motion works is a little different. First of all, you draw a straight line. Okay, and the first question, we're just going to work with this position function, and it's asking you what is the total distance traveled from 0 to 4 seconds. So what I'm going to do is make a table and take a look at when t is 0, 1, 2, 3, and 4. And the quickest way to do that is to put this in the table in the calculator. So I'm going to do that. Okay, so I went to table, edit function, and I just put that in there. Now I'm going to hit enter, and I'm going to start at 0 and do count by ones and do auto. And so I can see I get 0, 0, 1, negative 13, 2, negative 20, 3, negative 9, and 4, 32. Okay, now the way this works is you're going to draw this on this number line. And the way it's going to look is you're going to put a dot at every y value, and it's going to follow along here. And the x value, basically just going to label it. So this is at time equals 0, the position is 0 meters. These are all meters. Okay, and then you're going to find the number negative 13 on the number line. And here's negative 10, so negative 13 might be right here. You put a dot there, and you can make it go that way, and that's t equals 1, but the position is on the number line. Okay, so how can you go a negative distance? Well, in this straight line motion, this negative 13 means you're going left in the left direction, 13 meters. Okay, and then so to plot the point to negative 20, you're going to go to the negative 20, put a dot, and that is at t equals 2. Okay, now here's something interesting happens. At 3 seconds, we are going to turn back around to get to 9 seconds. So there's got to be this turnaround like this, and we want to go to negative 9 seconds. All right, so you can imagine this little bug going left to 13 meters and then left to 20 meters and then turning around and going back to the right, but you're still at the negative side. All right, and then at 4 seconds, it's all the way over to 32 meters. So that would be all the way over to that. And so that is what a straight line motion graph looks like. Okay, now to answer the question, we have to think about the movement, not the signs, but the movement, okay? So the total distance would be from 0 to 1 second, he moved left 13, so that little fella, whatever is moving, would have moved 13 meters. And then from 13 to 20 on the left of 0, that's 7 meters. And then this is strange. When you have left 20 and left 9, you turned around, but you went 11 meters because 20 take away 9, same side, so you just drop the negatives. 20 take away 9 is 11. All right, now this is weird. From -9 to 32, you cross over 0. So I'll break this up. So at -9 to 0, you went 9. And then from 0 to 32, you went 32. So if we add all of those up, that's 20, 31, 40, that's 72 meters is the total distance traveled. So that's a little different. That's how you do straight line motion. Okay, let's keep going. This is a very important example. You may see it again. All right, second example, or second question says, find the velocity and acceleration as functions of t. Okay, so the velocity function will be the derivative of this position function. So that would be 6t squared minus 6t minus 12. And the acceleration function would be the derivative of velocity, which would be 12t minus 6. Okay, now we're going to use these. All right, so it says find the time when the object is stopped. Okay, so if you look here, moving, and there's some turning around right here. So we might think the object is stopped right here. Well, do you remember how we found where the object reached its maximum height? That happened when we changed from going up to going down. And that happens when your slope is 0. So that's exactly what we need to remember here. And that is, to find when the object is stopped, we are going to set the velocity equal to 0. Okay, so that's 6t squared minus 6t minus 12 equals 0. And I can divide everything by 6. So that's t squared minus t minus 2 equals 0. And that's easy to factor. That's t minus 2, t plus 1. So that's t equals 2 seconds, or t equals -1 second. Now, you can travel with negative values because that just means you're going left, but you can't have negative time, so you can cross that out. Okay, so this is a critical point. This is a change. We know that this is where the object is stopped. All right, and then it's going to ask, when is it moving left and moving right? So what you can do is, once you find where it equals 0, that's called a critical point, what this is asking you is, when is the velocity less than 0? And when is the velocity greater than 0? So basically, you're solving a quadratic inequality. And the way you solve a quadratic inequality is, step 1 is you find the zeros. And that's a critical point because that's where things are changing. And we'll go ahead and put -1 as a critical point here. But we know this is t, so we know that we can't have anything less than time of 0. But what I'm going to do is I just want to show you, what you do is you take those critical points and you draw a line through them. All right. And then to the left of this, you can do this a couple of ways. Just put a number, pick a number, -2, and you can plug it in here and you would get a -2 minus 2 is a negative. And then times a -2 plus 1 is a negative. And so that's a positive. Or you can think about the shape of this quadratic and you can see it's positive. Now, if you put 0 in here, you're going to get a -2 times a +1, you're going to get a negative. Or you can look at the graph and see it's below. And then if we put a test number in here like 3 take away 2 is a positive, and 3 plus 1 is positive, so you get a positive. So now we know how every time, and so now we can get rid of that, because the only time we care about is the time at 0 or beyond. Okay, so Now we can see that the velocity is negative between 0 and 2. Well, that doesn't mean anything but moving left and right, and so our graph verifies it. You can see that we were moving left. The velocity is negative. We were moving left until we got to t equals 2, and then we moved right. So when is the object moving left? When the velocity's values are negative. So between 0 and 2, the object is moving left. And between 2 and infinity, the object is moving right. And I should put units because it's important. I'm going to add that between 0 and 2 seconds, and between 2 after 2 seconds. That's better. Okay. All right. Next thing, find the time when the acceleration is 0. Okay, so that means we're going to set this acceleration function equal to 0. So 12t minus 6 equals 0, 12t equals 6, t equals 1/2 seconds. Okay, so what that means is we can use this to find out whether we've got acceleration or deceleration. Okay, so I have to tell you quickly, I think it's not doable unless I tell you this, that the second derivative doesn't really tell you whether it's accelerating or decelerating or not. It tells you about the concavity. And if the second derivative is positive, it's concave up. And if the second derivative is negative, it's concave down. All right. And so what does that mean? Well, we want to know whether we are accelerating or decelerating in the next page. Okay. So you have to know about concave up and concave down, in my opinion. So concave up is if you take a wire and you bend the ends up like that. That's concave up. So that would mean the acceleration is positive. But it also might look like this, something like that. That's what concave up looks like. And concave down is if you take the ends of the wire and bend it down. So that would be if the acceleration is negative. Okay. And so I'll tell you why that's important. But let's go back to this. All right, so we want to find the time when the acceleration is 0. So that's at 1/2 seconds. We did that. And then we want to find the acceleration at the instances when the velocity is 0. Well, we found the one time the velocity was 0 was 2 seconds. So we can find a of 2 by plugging 2 into the acceleration function, which is 12 times 2 minus 6, which is 24 take away 6, which is 18. And now let's do some units. Acceleration is going to be, where are my units? Wait, I didn't write them down. We did, it's seconds and meters. So acceleration is going to be meters per second squared. And notice that it's positive. So that doesn't tell me whether acceleration or deceleration, it tells me concavity. So this is concave up. Okay. All right, let's explain why that's important to me. All right. So find the velocity and the acceleration after 1 second. All right. And then here it is. Is the object speeding up or slowing down? So speeding up means accelerating. Speeding up means the rate of change is getting faster. Okay, slowing down means decelerate. Okay, so find the velocity acceleration. Let me copy down this velocity function here. Let me pause it. All right, here we go. We want to find the velocity after 1 second. So we put that in and we get 6 take away 6 minus 12. That's minus 12 meters per second. And then we want to find the acceleration at 1 second, and that's 6 meters per second squared. And it says describe the motion at that instant. All right, well, what you can do is you can think about, remember, this is the slope of the tangent line. So, and this is telling you which way the object is moving. So the object is moving left at a velocity of negative 12, or speed. The left takes care of the negative, of 12 meters per second squared, per second. Okay, now what's happening with the acceleration? All right, we call this the acceleration function, but here's the trick. If these two signs are different, it's decelerating. All right, so the object is decelerating at a rate, it's still a rate, of 6 meters per second squared. And that's why I had to tell you about concavity, because it messes people up. This positive doesn't tell you acceleration, it tells you about concavity. All right, so what's happening is this object is moving left at a velocity of negative 12, or a speed of 12 meters per second, but it's moving, but it's decelerating, slowing down. All right, so that's this question. Is the object speeding up or is it slowing down? Okay, so if the signs are the same, if V of t and A of t have the same sign, then it's accelerating. And if V of t and A of t have different signs, then it's decelerating. All right, now I can kind of explain, looking back here, this A of t tells you about concavity, but just literally look at what this line, what is the slope of this line here? See, that function it's going down, it has a negative slope. So this is a velocity function. Velocity is going down, but acceleration is going up. So that would be negative, positive. This is actually deceleration. And you can see it. Imagine that it's a pebble. It's going really fast, and then it gets to the bottom of the hill and it starts to slow down. Okay. Here you got positive slope. So this is velocity would be greater than 0, and acceleration is concave up. So this is acceleration. Here, concave down, you can see the slope is negative, so V of t is negative. So this is actually acceleration, because the signs are the same there. Here, this is concave down, so acceleration is negative, but you can see the slope is positive. So this is actually deceleration. So basically what you need to remember is, if the signs are the same, you're accelerating. If the signs are different, you are decelerating.